And Professor Ho, we have many other chances to meet and talk, but today's talk is very special. He talked about his whole life and what's. I hope we can learn many things from him. And I am also at the age to looking back. So looking back, my career life and the family life, in fact, has been affected by Professor quite a lot. And academically, of course, I learned from many things. And this talk will summarize how can I working on my whole life. Some students asked how Professor Ho motivated the students. I think Professor Ho motivates the students by his great ideas. We know that he works for 4 areas. And fortunately, I am working on one of his early. For the whole life, for my own all the research, I cannot see any work, significant work, which is not comes from the original idea. So I will show how can his idea support me for the whole life, and even more, I don't have time to finish all this research. The topic is again the perturbation analysis, but I will show you how perturbation analysis and the principle leads to all the way to now, which I think opens up a new vision, complete new vision to the whole area of perturbation or optimization. To talk about this, let's back a little bit. Let's look at what the optimization problem is. That is what the problem we are facing. In fact, if you really think about that, most of the problem we are facing just comes from the fact that the state space is too large. Suppose we have all this policy, right? Policy depends on states exponentially. So you cannot conquer all this policy. If the policies are finite or small number for policy, you can evaluate every policy and compare it with them with the computer. That's it. But because the exponential growth of the policy numbers, we cannot do that. Even with the any future computer, we cannot do exhaustive search. Because a famous example is if we only have 2 actions, 100 states, the policy was 10 to the 30 squares. Even use the computer, and you need 10 to the 12 square years to count that. You cannot expect that any computer in the future can solve this problem. So as optimization, we still have our long way to go. This is the only problem. So exhaustive search is not possible. However, we still have to do our work, right? Perturbation analysis is one way to solve this work. The essential idea, Professor Sanders already mentioned what perturbation analysis is, but we can view that seems to me very essential idea is with the spatial structure of a system. Without, if you do not know any structure of the system, you can do nothing except the exhaustive search. With the spatial structure, by analyzing one policy, we can obtain the performance of its neighborhood policy. This is the essential idea of the perturbation analysis. In the early days, it's queuing system. We use the queuing structure. We can develop very accurate, efficient algorithm to get the derivatives. Why we can get the derivatives? Because we can predict the very close policy, what it will behave. If we perturb a little bit, what the new policy will behave, then we can do grading, then with grading we can do the hill climbing, we can find the best policy. We don't have to care about all the other policies. Then the question naturally to ask, if discrete policy, how about the two policies are too far away? So if we extend the idea of perturbation analysis, you can view it in this way. With some special structure, by analyzing one policy, can we find a better policy? Which is the idea of policy iteration. In fact, the policy iteration, we can view that as a discrete version of PA. Because if you analyze one policy, you can find another policy which is better. Then you can analyze that policy and do it again, like hill climbing. This is iteration, policy iteration. Again, you need to use the special structure of the system. It turns out the Markov system, the structure of Markov, allows us to do this. So we have two things. One is a continuous system. We do perturbation analysis. Perturbation analysis is based on performance derivatives. We can get the performance derivative. If for discrete case, we have the performance differences. Analyze one policy. I will give you an example. How can we tell from the performance difference equation? We can tell how to find a better policy. So we can find a better policy. We can find a better direction in this continuous case. We can do hill climbing. We can do policy iteration. And if the gradient equal to 0, then it's a local optimum. If we cannot find any better policy, then it's global optimum, which gives us the HRB equation. So we have the perturbation analysis here, this approach, because it's different from the dynamic programming. Recently, I named that as a relative optimization. All things depend on relative comparison. So my conclusion is that PA and relative optimization probably are the only way to overcome the difficulty in exhaustive search. The idea is, if you cannot do this, if you compare two policies, you need to analyze the two policies. Then you get the optimal, you have to analyze all the policies, which is the exhaustive search. Only if you can analyze one policy, you can get something about the other policies. Then you can save the time. You do any optimization theory. So in my view, any optimization theory is based on this principle, which I call the comparison principle. In fact, H-Jack-B equation fits this idea. In fact, you only analyze one policy, get the value function or potential function, you can find another best policy. So the relative optimization theory, let's compare with dynamic programming. Dynamic programming, I assume all of us know this. It basically works backwards. From time k plus 1, you go back. If you find the optimal policy in k plus 1, you go back to step k. You get the optimal policy of step k. However, one disadvantage of this is it only gives you local information, step k. So it cannot solve the, for example, called the under-selectivity issue. Under-selective issue, what is that? For time non-homogeneous system, the long-run average does not depend on any policy in the finite period, right? Because it's long-run average, you go to infinity. If you use dynamic programming, you treat every stage in the same way. So you cannot, definitely you cannot handle this. Okay, this is one disadvantage. Stochastic control. In stochastic control, it's even clear. you work from time t plus delta t, you go back a little bit, then you get the partial differential equation for that. Partial differential equation, we know it's a local information. Certainly you cannot deal, it's a differential equation, certainly you cannot deal with non-smooth value function. Right, it's naturally limited by dynamic programming, which is a big problem in stochastic, in recent and current stochastic control. People use the mathematician, again goes to the mathematician, they use viscosity solution. Honestly speaking, I read the box papers of viscosity solution. I know very clear mathematical definition is, I have no insight behind that. It's just use approximation, use two function approximate that. You lose the insight, then you cannot thinking how to go on. I will show you if you use the relative comparison, everything becomes clear. You can further do many research. So dynamic programming, as I just said, works backward in t plus delta t to t. It gives you local information. What is the weakness? It's not convenient for long average. You have to go to time, go to infinity, or you introduce visual states, whatever, you have all this technique. Again, you lose the insight. Second, you do not work for non-smooth value function. You use viscosity solution, then you stop it there. Degenerate processes are not very well explored because it's not smooth. Value function not smooth. Again, it's not necessarily a condition. It's under selectivity. It's not necessarily sufficient. There are many other problems we know dynamic program cannot solve, like nonlinear problem, whatever. Okay, let's say a little bit more about this relative optimization, because the PA, we are very familiar with that. Let's say what about the discrete time. Discrete time, the PA, this direction where I first work on extending the perturbation analysis to Markov processes, which is in the 90s, I started to work on this problem. Then from the original sample path, the red one, if we perturb the transition probability a little bit, you can introduce perturbation. In discrete case, the perturbation becomes a jump of the states. Original state is I, then because of the change of transition probability, it becomes J, then you compare the effect of each jump, then you add them together, you get the perturbation, the derivative. At that time, I talked with Professor Ho. It was his one question. I think about 5 years, then get the solution, then post on the research. He says, I extended to the find the difference. He said, do you have intuition for that? I just mathematically works on from the perturbation analysis to the sensitivity analysis. I said, honestly, I didn't have that. Then I really think about 5 years. I gave a very nice intuition. Today I will not give that, talk about that, but I give you the results. Because it's too technical details. It's 5 years. Yeah, the idea is you compare two, in discrete case, you compare two policies, the sample path of two policies, directly. Do not go into dynamic programming. You compare two sample paths. PA is a sample path-based idea, I will know, so I extended to Markov system optimization. So we have two policies, D and D prime, then we wanted to compare the two policies. I will give you examples. For example, time non-homogeneous Markov chain. time non-homogeneous, even the state space may be different at different k. So transition probability metric is different. This may not be square. Okay. So I will have this subscript k to describe the steps. I have two policies. This is transition probability matrix. F is the reward. Eta is the performance, long-run average performance. The value function or the potential function is called G. I remember Professor Wen's teaching. A slide cannot contain more than five notations. Otherwise, people cannot remember. So I examined this. It's exactly 5. I think it's the limit for you to remember. Let's go it again. This is Markov time corners. We have transition probability matrix P sub k. We have reward Fk. We have long-run average eta, which is the long-run average of the reward. Then we have the performance potential, which is a solution to the Poisson equation. It is very easy to develop this difference equation. I do not go to the details, but you can look at the form. In this differential equation, we only need to solve, I have two policies. You only need to solve the Poisson equation to get the G for one policy. There's no prime G. Others are parameters. Non-primary, you don't need to do any calculation. So in order to, this fits my comparison principle, in order to compare two policies, you only need to analyze one policy, which involves calculation. You need to use a computer. So by this difference equation, it's very clear. Eta prime is less than eta if every item is less. This is the HW equation. If this is less than this, right? You only need to solve the value function G, potential function G. Then by this simple calculation, you can find a better policy. If this all equal to 0, then you get the optimal policy. If this is, if you have one policy which is bigger than any other policy, this is the optimal policy. This is the HW equation. Simply look at the difference equation. You do not need. Okay. Under selectivity, very clearly, you don't need because it's long-run average. The difference is long-run average. The HW equation do not need to hold for any finite period or any subsequences. The frequency is 0. Okay, it's so simple, so clear. Now we talk about stochastic control because for the recent 7 years I'm working on the stochastic control because I published a book in 2007 which covers the discrete case of this relative optimization. Then the question is how about the stochastic control? Continuous time, continuous state space. This is why I jump into financial engineering because that's the most application years. So it motivates my idea. So we have differential equation, stochastic differential equation. You don't need to look into details. The problem is you have Brownian motion. We all know the Brownian motion, right? We have finite horizon control problems. If you know stochastic process, you know Ito equation. This is the fundamental equation. If a function eta of x, if you get a derivative, you not only need the first term, you need the second order derivative, right? This is Ito equation. In fact, this is used in dynamic programming. We'll get the HRV equation. Because of this approach, naturally we need a second order derivative. Then the whole series sticks there. if it's not differentiable, then we put a pad here and say, so viscosity solution comes here. In fact, if you use another equation, called Ito-Tanaka formula, it shows if it's non-smooth, instead of the first term, you have the second term. This is the sided derivative, one-sided derivative. If this was left side derivative, the right side derivative are not equal, then this term is not zero. This term is called local time. This get indeed a little bit technical, but let it give you the idea. The local time, in fact, is at the order of square root of delta t. It's not delta t. So compare with delta t, square root of delta t is infinity. Also, the non-smooth point might be at a measure 0, but this is infinity. This term you cannot ignore. But you cannot get derivative of this because this. How can you get derivative? Because it's infinity. Hey, use our differential equation. You can easily get this differential equation. It shows instead, in addition to the HJB equation, first time is continue for the smooth point. Second time is this non-smooth point. It shows for the smooth point, you need the HJB equation. For the non-smooth point, you need this condition. Very simple, very clear condition. You don't need a viscosity solution. Okay. The only problem is because the order of square root delta t you lost, which is infinity. Right. Why is this? This is a simple example. If this is a Brownian motion, usually a stochastic involved the Brownian motion. If it's a smooth function, then the expectation of dt is 0. If it's non-smooth function, a typical example is the absolute value of x, then we need the expectation of dwt absolute value, which is at 0 is square root of dt. This term cannot be ignored, although it happens very rarely. And if we use our differential equation, we can easily solve that problem. When I give presentation to the financial engineering people, because control people nowadays do not pay much attention to stochastic control. So I make presentation to financial engineering people. They say, idea is good. What's the applications? What problem you can solve? I said I solve this to under selectivity, and it's not a real problem. So they are looking for a real problem to have solution. But I only worked for one real problem with Wang Xiangwei. So we worked together for real work. It took me already two years to solve a nonlinear problem. In fact, it goes back to the perturbation analysis. I don't have many 2 years. So I hope someone can work on the applications. It opens a new way to view the optimization. If others' work does not work, try this one. I can offer advice, but the problem you have to work out. This almost last slide. It's a summary. Relative optimization, which stems from perturbation analysis, same idea from analyzing one policy to the performance of the other policy, gives us global information instead of local information. It solves the under-selectivity and the non-smoothness. Viscosity solution is not needed. And I worked many problems on the degenerate process because it's related to non-smoothness can be expanded in a lot of details. And it gives you a clear picture of the long-run average. We even can do state classification. For this, it's surprisingly for this stochastic control, stochastic processes, seems to me I cannot find any work on the multi-class, even state classification, because people do not talk about the generator. We have bias opportunity, we have multi-class optimization, all this comes out. And the insight, we can give an insight from new research. Very simple summarize. Performance optimization, okay, we have a performance optimization. Usually we go to the dynamic programming, which you jump too far. Because of its limit, it has its disadvantages. Then you get HRB so far. But if you go back a little bit, you think about just comparison, relative optimize, you probably can get more. So here I remember Einstein's quotation. It says, if you solve a problem at the same level of it was created, you cannot solve the problem. That means for many problems, the problem comes from dynamic programming itself. If dynamic programming cannot solve some problem, you still think about in that framework, you cannot solve the problem. It creates itself. So you have to back up to think about some other way. Thank you.